Today topic is torsional circular shaft. It is a syllabus. So first of all, I would like to discuss about bar and beam. If you know the bar and beam differences, then you can easily understand this topic. So here, bar is nothing but it is a structural member. So let you consider it as a member. So let you consider the beam. Beam is also same member you can consider. If the first member, this is called bar, right? So this you can call as a longitudinal axis. This you can call as a again longitudinal axis only. If we apply the load along this direction, this is Fx, or if you apply the moment along this x-axis, this is represented by Mx. This type of members you can call as a bar. Whereas here, so perpendicular to the axis, otherwise longitudinal axis, you can call this as a Fy. Okay, so and also you can represent with My, and we have another possibility that it is perpendicular to the longitudinal axis Fj, and perpendicular to the longitudinal axis moment is Mj. So this is beam, this is bar, that's it. So when any member is subjected to axial loadings, you can call that as a bar. Transverse loading, these two forces are transverse forces, two moments are transverse moments. So when a member is subjected to transverse moment, you can call that as a beam. So the torsion you can call that comes under bars only. So when a bar circular cross section member, it is a longitudinal axis of the member, is subjected to twisting moment, so that is torque T, which you can also represent with Mx, which should be along the x-axis. You are going to apply a moment, and one end is fixed. So this is called torsion on a circular cross section shafts. So this is about bar and beam. So let you consider it is the shaft. So same thing I would like to draw the diagram here. So it is a circular cross section shaft. So one end is fixed here. So let you consider this point is somewhere here. I'm considering some point A. So I'm going to draw a line here. So this point I'm going to consider as B. So I'm going to represent here. So it is the center of the cross section. I like to draw the center of the cross section again here. So if I draw a line, this is called longitudinal axis. Along this direction, you are going to, along this direction, you are applying the torque. So the B point changes from B to B dash actually. This is B dash, this point is B. So same thing I would like to represent here. This point is B, whereas this point is, you can call it as a B dash. So the inclination, this is called theta. This theta you can write it as, means you can call it as an angle of twist. It is in radians always. So angle of twist. So from this, you can consider that it is the R, that is radius of the shaft. It is varying from 0 to capital R. Means the value from the center is 0, at extreme position it is going to be capital R. And from this relation, you know already L is equal to R theta. From this cross section I'm considering. So L is B dash, which you can equating, and R here it is capital R into theta as it is. It is a relation we got. And from this diagram, you can observe that here we can consider this is phi inclination. So from this diagram, from the front view, if you apply the tan phi, opposite side is B dash divided by AB. So here the AB is length of the shaft. Initially you have to consider that is L. So you can write it as B dash divided by AB is L. But B dash already we had the value, that is R theta divided by. But tan phi, here the phi value is very small value, and also you can observe that here the shaft is, when the shaft is subjected to torque, the member is distorted. So you can observe that inclination as a shear strain. So directly I can represent, because it is a small angle. So whenever the tan phi is small, so which equating to phi only. So finally you could represent the shear strain. Shear strain is equal to r theta over L. So we consider that one assumption that it is ready to follow the Hooke's law. So that's why the tau is proportional to shear strain. So otherwise tau is equal to G into shear strain. So same thing you can substitute. So therefore tau is equal to G into r theta over L. So therefore finally we got tau divided by r is equal to G theta over L. So it is the first relation we had got. So the first relation, that is tau by r is equal to G theta over L. So here one thing you have to observe that, so the tau is having maximum value because r is the maximum value. So for that one, I can write one relation as tau at some instant position and r is read as some instant position. It is going to be taken as G theta over L. So the tau is proportional to r actually, means we have a relation between tau and r is linear. So that's why if we draw this cross section again, so it is a circular cross section of the shaft. So when the r is 0, tau is also 0. When the r is capital R, so the smaller value vary from 0 to capital R only. 0 to capital R only. So at capital R, it is having maximum value. At smaller, it is having minimum value. So it is a shear stress distribution in the shaft when the shaft is subjected to torque. So opposite to it, you have a shear strain again, and it is represented in this direction. So here is the tau max. This is tau max at t r is equal to capital R. So let you consider the cross section. The cross section will be same as it is. So it can be taken as, I'm going to consider the cross section here, same circular cross section. So it is the center of the shaft. So I'm going to consider a small strip over it. So again, it is having some thickness. The thickness of this one, from here to here, I'm considering small r. I'm going to consider small strip here. From here to here, it is capital R. Okay, it is totally a small strip. So you know when the torque is applied on the cross section, means it is subjected to twisting moment over the cross section. So let you consider, is the cross section you consider. Okay, so the twisting moment, you can write it as force multiply perpendicular distance. Here the force you can represented in the manner of shear stress. Shear stress into dA. Okay, over this cross section only I am considering. Over this cross section, shear stress into dA, because already we observed the cross section shear stress distribution over the cross section, that is tau into dA multiplied perpendicular distance from here to here is small r. This is nothing but torque. So but it is in limit from 0 to capital R. So capital R, so that's why you have to apply the integration over it. So it is 0 to capital R tau dA into small r. So in place of tau, we can substitute this value as it is. So therefore, T is equal, in place of tau, you can substitute G theta L by L into R. So it is G theta R divided by L into R into dA. So this total value, same thing I had written here. So therefore here G theta L is constant, integration of R square into dA. So this integration of R square into dA, you can write it as polar moment of inertia. So therefore G theta J divided by L. So finally we got the equation, that is T by J is equal to G theta over L. Already we have the relation, that is T by R. So this equation you can consider as a torsion equation, and it is applicable for only circular cross section. Here T is nothing but twisting moment, J is nothing but polar moment of inertia, and G is rigidity modulus, theta is angle of twist, L is length of the shaft, tau is shear stress, and R is radius of the shaft. That's it. In the next class, we are going to discuss the remaining things.